Right now, at the exact center of the Milky Way, a monster is sleeping. It has been sleeping for a long time. Long enough that every civilization humanity has ever built, every empire that rose and fell, every language spoken and forgotten, every war fought and concluded, all of it occurred during this single unbroken silence. The black hole at the heart of our galaxy has not made a sound, not by any measure that reaches us in longer than recorded history extends. And yet, the silence is wrong. A black hole containing 4 million times the mass of our Sun sits surrounded by more gas, more stellar wind, more raw cosmic fuel than it could ever consume in a billion years. By every equation physicists have written, by every model astronomers have constructed over the past half-century, Sagittarius A times should be screaming. It should be blazing with the light of 100 billion suns. It should be visible across the universe, a beacon announcing itself to any civilization with a radio receiver pointed in the right direction. Instead, it whispers, it flickers. It produces, in terms of raw energy output, less radiation per second than some ordinary stars scattered across our own spiral arm. The silence is not peace. It is a held breath. Here is what most people do not understand when they learn that a supermassive black hole lives at the center of our galaxy. They imagine something violent, something perpetually consuming, endlessly devouring, screaming with the light of matter being annihilated at the edge of an event horizon. That image is real, but it describes other galaxies. Distant systems where the central black hole feeds with a ferocity that outshines every star in the host galaxy combined. Those objects are called quasars, and they are among the brightest things in the observable universe. Some of them are so luminous that their light has been traveling toward us for 13 billion years, and we can still detect it with a modest telescope on a clear night. Our black hole produces roughly 100 million times less energy than it theoretically could. 100 million times less. The number is so extreme that it ceases to function as a number and becomes instead a statement about the nature of something fundamentally strange occurring at the gravitational heart of the Milky Way. But here is what makes this silence truly disturbing. It is not permanent. We know this because the evidence is written across thousands of light years of glowing gas in X-ray fluorescence, echoing off molecular clouds in two enormous structures extending above and below the galactic plane that require energies so vast. No sleeping black hole could have produced them. Sagittarius A times has woken before. The scars of its last awakening are still visible if you know where to look. And every piece of evidence gathered by every observatory we have pointed toward the galactic center suggests that the conditions for another awakening are slowly, patiently, inexorably assembling themselves. The question is not whether it will wake again. The question is what happens when it does, and whether the universe has left us in exactly the right place, at exactly the right distance for that moment to be something we can witness rather than something that ends us. If you find yourself drawn to the kind of journey that takes a single question and pulls it until the entire architecture of the cosmos comes into view, do something small for this channel. Hit the like button and subscribe. It costs you nothing, and it makes a genuine difference. Now find somewhere comfortable. Clear your mind of everything except what lies 2,600,000 light years away in the direction of the constellation Sagittarius. Let's begin. To understand why the silence of Sagittarius A times is so deeply wrong, you first need to understand what it is. Not in the abstract way, the phrase supermassive black hole usually gets used as though the words themselves carry sufficient weight. You need to feel the scale of the thing. And scale, when it comes to the galactic center, requires patience and a willingness to let numbers do something unusual, to stop being numbers and start being physical realities. Our sun is not a small star. It contains 99.8% of all the mass in our solar system. Jupiter, the largest planet, the gas giant so large that more than 1,000 Earths could fit inside it. Jupiter amounts to a rounding error when placed next to the Sun. The mass of our star is so dominant that every other object in the solar system, every planet, moon, asteroid, and comet exists essentially as debris orbiting a single gravitational center. The Sun is, for the purposes of our local cosmic neighborhood, everything. Now, Take that sun, multiply its mass by 4 million, pack every gram of that mass into a sphere smaller than the orbit of Mercury, smaller than the distance from here to the nearest planet in our sky on a winter evening. The density required to accomplish this exceeds anything that exists in ordinary matter. No arrangement of atoms, no exotic state of nuclear material can survive at those pressures. Space itself warps so severely around this concentration of mass that the normal rules of geometry stop applying. Distance and time bend. Light that crosses an invisible boundary called the event horizon cannot return. It is not slowed. It is not weakened. It simply ceases, as far as the observable universe is concerned, to exist as light traveling outward. It falls forever. That is what sits at the center of the Milky Way. 4 million solar masses compressed into a volume your solar system could contain, a point where the equations of general relativity, the most precisely tested theory in the history of physics, approach their limits. A place where the curvature of space-time becomes so extreme that even our mathematical descriptions of reality begin to strain, and it is surrounded on all sides by fuel. The galactic center is not empty space punctuated by a dangerous object. It is the most densely populated region of our galaxy. In the neighborhood where our sun resides, the average distance between neighboring stars is roughly 4 light-years. You could place entire solar systems end to end in the gap between us and the nearest star and still have room remaining. The stellar density around our sun is by galactic standards almost rural. Near Sagittarius A times the geometry is completely different. Within the central 3 light-years, a volume you could traverse at the speed of light in less time than some human civilizations have existed. Thousands of individual stars crowd together. The average distance between neighbors drops from light-years to fractions of light-years. Gravitational encounters that would take billions of years to occur in our stellar neighborhood happen here within mere thousands of years. Stars pass close enough to exchange energy to alter each other's orbits, occasionally to collide entirely. The environment is violent in ways that have no parallel anywhere in the galaxy accessible to human observation. And threading through this stellar crowd, filling the spaces between stars flowing in vast sheets and spiraling currents toward the gravitational center, is gas, molecular gas, ionized gas. Stellar winds shed by massive stars living out their brief, furious lives in the radiation bath of the galactic center. Clouds of hydrogen and more complex molecules orbit the black hole at distances ranging from a few light-hours to several light-years. If you gathered the gas within the inner 10 light-years and weighed it, you would count tens of thousands of solar masses of potential fuel. By every right, Sagittarius A times should be consuming this material at a rate that produces luminosity comparable to the brightest objects in the observable universe. The fuel exists. The gravity exists. The geometry exists. A black hole of this mass, accreting at its theoretical maximum, would outshine every star in the Milky Way combined by a factor of roughly 100 billion. Our night sky, if Sagittarius A times were feeding normally, would not be a field of scattered points of light. The galactic center would dominate everything visible, punching through the intervening dust, with enough energy that even the wavelengths that dust absorbs would scatter enough to make our sky glow. Instead, we have silence. The first hint that something unusual existed at the center of our galaxy came not from a telescope pointed at the sky, but from a rotating antenna mounted on wheels taken from a Model T Ford. In 1932, a Bell Telephone Laboratories engineer named Carl Jansky was tasked with identifying sources of radio interference, disrupting transatlantic telephone communications. He built a directional antenna array. His colleagues called it Jansky's merry-go-round, and began cataloging every source of static he could detect. He found interference from nearby thunderstorms, distant thunderstorms, and then something else entirely. A signal that did not move with the sun, but instead tracked the stars. A persistent hiss of radio emission that peaked with clockwork regularity whenever his antenna pointed toward the constellation Sagittarius. Jansky had accidentally invented radio astronomy, and in doing so, he had detected the first whisper of whatever lurked at the heart of the Milky Way. He published his findings. He moved on to other work. The discovery sat largely unexamined for years, waiting for the world to develop instruments sensitive enough to follow the thread he had found. That moment came after the Second World War, when the radar technology developed for military purposes was repurposed for scientific observation. Radio telescopes of increasing sensitivity began mapping the galactic center region in detail that Jansky's equipment could not approach. The emission from the galactic center proved to contain multiple components: a supernova remnant, spiral structures of hot gas, and at the very center, a compact radio source unlike anything else in the sky. A point-like emitter producing radio waves from a region smaller than our solar system. That source was named Sagittarius A, times with the asterisk denoting its unique character, the astronomical convention for particularly notable radio sources. For decades, astronomers debated what Sagittarius A times could be. The compactness was striking. Something producing that much radio emission from that smaller volume suggested enormous energy densities. The most dramatic hypothesis, that a supermassive black hole sat at the center of the galaxy, seemed almost too extreme to accept without direct confirmation. Black holes were still controversial objects in those years, mathematical solutions to Einstein's equations that many physicists suspected nature might find ways to avoid. Confirmation came through patience, through years and then decades of watching individual stars orbit the radio source. Beginning in the 1990s, two independent teams, one led by Andrea Ghez at the University of California, Los Angeles, one led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics in Germany, began using infrared telescopes to pierce the dust obscuring the galactic center and track the positions of individual stars orbiting close to Sagittarius A asterisk. The results were in the strictest sense of the word shocking. One star, designated S2, completed a full orbit around the central radio source in 16 years. 16 years. Our own sun takes 230 million years to complete a single orbit around the galactic center. S2, a star, comparable in mass to our sun, orbits so fast that a single human lifetime contains nearly 4 complete circuits. At its closest approach, S2 passes within 17 light hours of Sagittarius A, times roughly 4 times the distance from our Sun to Neptune while traveling at speeds exceeding 15 million miles per hour, 3% of the speed of light. No star anywhere else in the galaxy moves like this. The orbital mathematics were unambiguous. To accelerate S2 to those velocities along that trajectory required a central mass of approximately 4 million solar masses concentrated within the volume S2 passed through. No collection of normal stars could pack that much mass into that smaller space. No exotic arrangement of dark matter or neutron stars could produce the required density. The only physical object consistent with the observations was a supermassive black hole. Ghez and Genzel shared the 2020 Nobel Prize in Physics for this work recognition of a discovery that transformed a mysterious radio source into a confirmed gravitational monster at the center of our cosmic home. But confirming the existence of the black hole and understanding its silence were entirely different problems. The confirmation told astronomers what Sagittarius A times was. The silence told them something was wrong with their understanding of how such objects behave. Because by the time the Nobel Committee recognized this discovery, the deeper mystery had already made itself apparent. The black hole was real, the fuel surrounding it was real, and the energy output was by every theoretical standard impossibly, inexplicably low. Like discovering that a fire burning at the center of a room surrounded by wood and oxygen produces no heat and no light. The ingredients are present. The physics should be unambiguous. And yet the monster at the center of the Milky Way sits in a silence that no simple equation can explain. The explanation, when it began to emerge, proved stranger than the mystery itself. And the first piece of that explanation arrived not from a telescope pointed at Sagittarius A times, but from 2 enormous structures that nobody had seen before. Structures that once discovered changed everything we thought we understood about the recent history of the most powerful object in our galaxy. 1710, Claude responded. In 2010, a team of astronomers analyzing data from NASA's Fermi Gamma-ray Space Telescope noticed something that should not have been there. In 2010, a team of astronomers analyzing data from NASA's Fermi Gamma-ray Space Telescope noticed something that should not have been there. Extending above and below the flat disk of the Milky Way perpendicular to the galactic plane were two enormous structures of superheated gas and high-energy particles. Each one stretched roughly 25000 light-years from the galactic center outward into the halo surrounding our galaxy. Together they spanned 50000 light-years from tip to tip, half the diameter of the entire Milky Way disk. They glowed in gamma rays, the most energetic form of electromagnetic radiation, produced by particles accelerated to extraordinary speeds and radiating as they moved through magnetic fields, threading the structures. Nobody had predicted them. Nobody had seen them before, despite decades of observations of the galactic center region at every available wavelength. They had been hiding in plain sight, partly because gamma-ray astronomy was still a young field, partly because the structures were so vast that identifying them required assembling a picture of the entire sky rather than studying a single targeted region. They were named the Fermi Bubbles. To understand what the Fermi Bubbles tell us about Sagittarius A, you need to understand the energy involved in creating them. The bubbles contain hot gas at temperatures exceeding tens of millions of degrees. They contain cosmic ray particles, protons, and heavier nuclei accelerated to near light speed, distributed throughout their volume. They contain organized magnetic fields producing the gamma-ray emission detected by the Fermi telescope. When physicists added up all of this energy content and asked what single process could have deposited it in roughly the configuration observed, the answer was both simple and staggering. The total energy contained in the Fermi bubbles exceeds the output of our Sun over its entire 10 billion year lifetime by factors of millions. Our Sun, which has been burning hydrogen into helium continuously for 4.6 billion years, which produces enough energy every second to power human civilization for tens of thousands of years, which is by any terrestrial standard an almost incomprehensible furnace, our Sun would need to run for millions of times its entire lifespan to produce the energy locked inside the Fermi bubbles. Something released that energy from the center of our galaxy, something enormous, and it did so relatively recently on cosmic timescales, because the structures have not had time to dissipate and blur into the surrounding intergalactic medium. The bubbles are still coherent, still sharp-edged, still organized. They are young enough, astronomically speaking, that their internal structure retains information about how they formed. The debate over what created them has continued since their discovery. Two primary mechanisms have been proposed. The first involves concentrated star formation near the galactic center, a burst of massive star formation producing supernova explosions at extraordinary rates, with the combined energy of millions of stellar deaths inflating the bubbles over millions of years. The second involves direct energy input from Sagittarius A times itself a period of active feeding, when the black hole consumed matter at rates vastly exceeding today's trickle, launching powerful outflows or jets that inflated the bubbles from the galactic center outward. The star formation explanation carries some plausibility. The galactic center does produce stars at elevated rates compared to most of the Milky Way. Massive stars there explode as supernova, with a frequency that has no equivalent in our quieter stellar neighborhood. But the energy budget strains this explanation. Producing the Fermi bubbles through supernova alone would require star formation rates so extreme that the galactic center would have been visibly extraordinary for millions of years, producing effects on the surrounding interstellar medium that observations do not fully support. The black hole explanation fits more naturally. A period of active accretion lasting a few million years, with Sagittarius A times consuming material at rates approaching the theoretical maximum, could have inflated the bubbles through radiation pressure and outflowing winds. The geometry supports this. The bubbles extend perpendicular to the galactic disk, exactly the direction you would expect material to escape if it were being driven outward from the galactic center by a powerful energy source at the core. Their roughly symmetric shape above and below the plane is consistent with a central engine launching outflows in both directions simultaneously. Most researchers now believe both mechanisms contributed with the black hole's past activity, providing the dominant energy source. If this is correct, Sagittarius A times was not always the quiet, almost invisible object we observe today. At some point within the past few million years, a cosmic eye blink in a galaxy 13 billion years old, the monster at the center of the Milky Way was feeding, actively, powerfully, with an energy output that dwarfs anything in our current galactic environment. And then it stopped. The transition from active to quiescent happened fast enough that the bubbles are still visible. If the activity had ended billions of years ago, the structures would have expanded and faded into the background. Their preservation tells us the feeding ended recently. The Milky Way's central black hole was a different kind of object within living memory of geological time. It was only a few million years ago that the last forests of the Miocene epoch covered regions now occupied by African savanna. Only a few million years ago that the ancestors of modern humans were beginning the evolutionary journey toward our current form. Our black hole's last major feeding episode may have ended around the time that the genus Homo was taking its first uncertain steps across the African landscape. The Fermi Bubbles are not the only evidence of recent activity. A separate class of observations conducted not with gamma-ray telescopes, but with X-ray observatories provides a timeline of Sagittarius A*'s behavior on much shorter timescales, decades much closer to the present, centuries, not millions of years. Scattered around the galactic center region lie molecular clouds, vast concentrations of cold, gas and dust, the raw material from which stars form. Some of these clouds sit tens to hundreds of light years from Sagittarius A, times well outside the immediate neighborhood of the black hole. When X-ray observatories examined these clouds, they found something unexpected. The clouds were glowing in X-rays. Not producing X-rays themselves, cold molecular gas does not generate high-energy radiation, but reflecting X-rays from some external source, much the way a white wall reflects light from a lamp shining elsewhere in a room. The mechanism is called X-ray fluorescence. When an X-ray photon strikes an iron atom in a molecular cloud, it can knock an electron from one of the innermost atomic shells. As electrons from higher shells cascade down to fill this vacancy, the atom emits a characteristic X-ray photon at a specific energy, 6.4 kilo-electron volts, a signature so distinctive that it serves as an unmistakable fingerprint for fluorescent ion emission. The clouds near the galactic center are producing this fluorescent signature in quantities that require illumination by a powerful X-ray source. Sagittarius A times is the only plausible candidate, but here is the crucial detail. The black hole currently produces nowhere near enough X-rays to explain the observed fluorescence. The illumination required is millions of times more intense than what Sagittarius A times emits today. Either the X-ray source is something other than the black hole, an explanation that faces serious difficulties because no other candidate exists with the required luminosity, or the clouds are reflecting X-rays from the past. Since light travels at a finite speed, X-rays reaching a molecular cloud located 300 light-years from Sagittarius A times would have left the black hole 300 years ago. The cloud reflects what the black hole was doing 3 centuries past, not what it is doing now. By mapping the fluorescent emission across many clouds at different distances and orientations from the galactic center, astronomers can reconstruct the X-ray output of Sagittarius A times at different points in the past. The technique is essentially a form of cosmic archaeology, reading ancient light preserved in the reflective surfaces of gas clouds scattered across the galactic center region. The picture that emerges from this reconstruction is remarkable. Roughly 300 to 400 years ago, as measured from Earth, meaning the actual events occurred 260,000 years before that, when light now reaching us first left the galactic center, Sagittarius A times was millions of times more luminous in X-rays than it is today. Not billions of times more luminous as it would be during a full quasar-like feeding event, but millions of times. The black hole was active. It was consuming material at a rate producing detectable effects across hundreds of light years, and then sometime after that, it faded back to its current near-invisible state. The fluorescent mapping does not show a single clean outburst and decay. The emission varies across different clouds in ways that suggest multiple episodes of elevated activity over the past several centuries, punctuated by quieter intervals. The black hole's recent history appears to be one of intermittent stirring, rather than continuous quiescence, occasional awakenings separated by periods of near silence, with the overall trend toward less activity over time. This intermittent behavior matters enormously for understanding what we observe today. The small flares that modern observatories detect from Sagittarius A times brief brightenings lasting minutes to hours occurring several times per day might be the fading remnants of a more active regime rather than the baseline behavior of a permanently sleeping giant. The question of whether the black hole is gradually becoming quieter over centuries, or whether the current quietude represents a temporary minimum before the next significant awakening, cannot be answered from a human-length observation baseline. We have been watching Sagittarius A times with modern instruments for only a few decades. Against a history spanning billions of years, a few decades is not even a breath. It was into this context a black hole whose silence was clearly wrong, whose past activity was written in glowing clouds and enormous gamma-ray structures, whose occasional small flares hinted at processes still operating beneath the apparent stillness that the James Webb Space Telescope was pointed in the months following its first science operations in July 2022. Webb launched on Christmas Day 2021, riding an Ariane 5 rocket from the Guyana Space Center on the northeastern coast of South America. The launch was the culmination of more than 2 decades of engineering work, scientific negotiation, and repeated delays driven by the extraordinary technical challenges of building the most capable space observatory ever constructed. The telescope's primary mirror, composed of 18 hexagonal gold-plated beryllium segments, measured 6.5 meters across more than twice the diameter of the Hubble Space Telescope's primary mirror. The gold coating was not decorative. Gold reflects infrared light with extraordinary efficiency, and infrared light was what Webb was built to see. The choice of infrared as Webb's primary observing wavelength was driven initially by the desire to study the most distant galaxies in the universe, objects so far away that their light had been stretched by cosmic expansion from visible wavelengths into the infrared during its journey across billions of light years. But infrared observation carries a second capability that proved equally transformative for galactic center astronomy. Infrared light penetrates dust, the same clouds of microscopic particles that completely block visible light, rendering the galactic center invisible to optical telescopes, no matter how powerful, allow infrared radiation to pass with only modest attenuation. Webb's golden eyes could see through the cosmic fog that had hidden the galactic center from direct observation for the entire history of human astronomy. Webb does not orbit Earth. It orbits instead around a gravitational balance point called the second Lagrange point, located approximately 1 million miles from Earth in the direction opposite the Sun. At this position, the telescope remains in continuous shadow behind a sunshield, the size of a tennis court, keeping its instruments at temperatures approaching -400 degrees Fahrenheit. This extreme cold is not an engineering curiosity, it is an absolute necessity. Infrared detectors work by measuring the tiny amounts of heat carried by infrared photons arriving from distant cosmic sources. Any warmth in the telescope itself would swamp these signals completely, like trying to hear a whisper in a room full of people shouting. Webb's cryogenic environment allows it to detect infrared signals so faint they would be invisible to any warmer instrument. When the first galactic center observations were planned, the science teams faced a challenge that had no parallel elsewhere in Webb's observing program. The galactic center is simultaneously one of the brightest infrared sources in the sky and one of the most complex. Thousands of stars crowd into the field of view. Gas and dust structures overlap at multiple distances along the line of sight. The black hole itself varies on timescales of minutes, requiring coordinated observations to capture transient phenomena. The region is so rich in sources that standard techniques for identifying and subtracting background emission required substantial modification. The scientific teams had prepared for years. When the data began arriving from Webb's position 1,000,000 miles away, transmitted to Earth via radio downloaded to the Space Telescope Science Institute in Baltimore, processed through calibration pipelines refined before launch, the initial reaction among the assembled researchers was silence, of a different kind than the silence of Sagittarius A times itself. It was the silence of people looking at something they had not expected and struggling to find words adequate to what they were seeing. Stars appeared where there should have been none. Gas glowed in ways that existing energy sources could not explain. Structures revealed themselves in the mini-spiral arms feeding toward the black hole that contradicted fundamental assumptions about how matter approaches an event horizon. And at the edges of the field, in locations so close to Sagittarius A times that previous theories categorically excluded the possibility, Webb detected the unmistakable signatures of stars in the process of being born. Not old stars that had wandered inward from safer regions, not the remnants of stars disrupted and consumed, stars forming, right now, in the shadow of the most powerful gravitational engine in the galaxy. The researchers asked for the data to be reprocessed. Instrumental artifacts, they assumed. Contamination from the overwhelming brightness of nearby sources bleeding into adjacent pixels. The calibration teams ran their procedures again. The results held. What Webb had seen was real, and it was about to force a rethinking of physical processes that astronomers had considered settled for decades. Because if stars can form in the immediate vicinity of a supermassive black hole, if life in its most basic cosmic sense can emerge from the most hostile environment our galaxy contains, then the silence of Sagittarius A times takes on a meaning far more complex than simple dormancy. The monster is not merely sleeping. Something is happening in its shadow, something that our equations did not predict and our theories did not allow. And understanding what that something is may be the key to understanding not just what Sagittarius A times has been, but what it is about to become. The tidal radius around Sagittarius A times is not a theoretical abstraction. It is a physical boundary as real as the surface of a planet beyond which the mathematics of gravity become absolute. Inside this boundary, a sphere extending roughly 1 light year from the black hole in every direction, the gravitational gradient becomes so steep that any extended object attempting to hold itself together will be torn apart. The force pulling the near side of the object toward the black hole exceeds the force pulling the far side by enough margin that internal gravity, chemical bonds, magnetic fields, and any other cohesive force known to physics cannot compensate. The object stretches. It elongates along the line toward the black hole, and then it shreds, pulled into a long, thin stream of debris spiraling toward the event horizon. This process has a name. Astronomers call it tidal disruption, and for decades the consensus was clear. Gas clouds entering the tidal radius of Sagittarius A times would be disrupted before they could collapse into stars. The same forces that would tear apart a comet, a planet, or a star would prevent the gravitational collapse required for star formation from completing. Inside 1 light year of the black hole, the physics simply did not permit new stars to be born. Webb found them anyway. Not just young stars that had somehow migrated inward from safer regions, not ambiguous sources that might be interpreted as stellar objects if you squinted at the data. Webb's near-infrared camera, operating at resolutions 10 times sharper than any previous infrared observatory, detected multiple objects displaying the spectroscopic signatures of protostars, stellar embryos still in the process of accumulating mass from surrounding material, still wrapped in the infalling envelopes of gas and dust that characterize the earliest stages of stellar birth. The signatures were unambiguous. Protostars emit characteristic infrared radiation produced when material falling onto their surfaces converts gravitational energy into heat. The spectrum of this emission is distinctive enough that astronomers can identify it across the galaxy, and Webb's spectrometers detected it at multiple locations within the central light year of the Milky Way. Take a moment to sit with what that means. Inside a boundary where physics says nothing should form inside the gravitational killing zone of a 4 million solar mass black hole, new stars are being born. not finished stars that have somehow cheated the tidal forces and arrived intact. Stars in the process of becoming cosmic embryos, gathering mass building toward the nuclear ignition that will make them shine, doing so in the shadow of an event horizon that should have prevented their existence entirely. The scientific community's reaction was not the excited celebration that sometimes accompanies major discoveries. It was something quieter and more unsettling. The reaction of people who have built careful, tested, mathematically rigorous models of a physical system and then watched those models fail at the most basic level. Not fail at the edges in some extreme regime where approximations might be expected to break down. Fail at the center, in the most fundamental prediction about what can and cannot exist near a supermassive black hole. Webb's near-infrared camera resolved individual stars in the galactic center region that previous telescopes had seen only as blurry merged sources. Objects that ground-based infrared observatories detected as single points of light, separated into multiple distinct stars when viewed through Webb's optics above Earth's atmosphere. The stellar census of the central parsec, a volume roughly 3 light-years across surrounding Sagittarius A times expanded by a factor of 5. Where previous observations had catalogued approximately 100 individual stars, Webb resolved more than 500. The galactic center's immediate neighborhood was 5 times more populated than anyone had realized. Within this expanded population, the protostellar detection stood out immediately. Several sources displayed infrared emission inconsistent with any stage of normal stellar evolution. Mature stars, even very young ones, that have recently ignited nuclear fusion produce infrared emission in characteristic patterns that Webb's spectrometers can identify precisely. The anomalous sources produced emission patterns consistent instead, with ongoing infall material still raining down onto a central condensation, releasing energy as it falls, heating the surrounding envelope of gas and dust to temperatures that produce the specific infrared glow of active star formation. If you shrank the distance from Earth to the galactic center to the length of a football field, the region where Webb detected these protostars would occupy a space smaller than your thumbnail held at arm's length. On the actual scale of the galaxy, we are talking about stellar births occurring within a cosmic hair's breadth of the most extreme gravitational environment our local universe contains. The proximity is not incidental, it is the entire mystery. These objects are forming where the black hole's influence is at its most powerful, not in some peripheral region where tidal forces are manageable, but in the heart of the forbidden zone. 2 competing explanations emerged immediately, and neither one fits comfortably within existing theory. The first possibility is that star formation can actually occur inside the tidal radius, through mechanisms that standard models do not account for. This would require some physical process to protect gas clouds from tidal disruption long enough for gravitational collapse to complete. The candidates are few, and each presents its own theoretical difficulties. Magnetic fields represent the most discussed possibility. The galactic center is threaded with magnetic fields far stronger than those found in typical star-forming regions elsewhere in the galaxy. Long filamentary structures of magnetized gas, extending for dozens of light-years, perpendicular to the galactic plane, structures detected in radio observations for decades, but still poorly understood, suggest that the magnetic environment near Sagittarius A times is unlike anything found in the quieter regions of the Milky Way, where astronomers have developed their models of star formation. Magnetic pressure can oppose gravitational stretching. If the fields threading a gas cloud are strong enough and oriented correctly, they might provide the additional structural support needed to resist tidal forces long enough for the cloud's self-gravity to complete collapse. The problem is that the field strengths required to accomplish this near Sagittarius A times would need to exceed anything measured in the galactic center region by significant margins, not by a small adjustment or modest correction to existing measurements, but by amounts that strain credibility. Whether magnetic fields of sufficient strength actually exist within the tidal radius, threading the specific gas clouds from which the protostars Webb detected are forming, remains unknown. Webb cannot directly image magnetic fields. It can only observe their effects on the gas and disentangling magnetic support from other physical processes in the chaotic galactic center environment is a problem that will require years of careful analysis. The second possibility involves extreme gas density. Tidal forces tear apart objects whose internal self-gravity cannot overcome the gravitational differential imposed by the black hole. For a gas cloud of given mass, this disruption depends on how compact the cloud is. A cloud of one solar mass spread across a light year will be disrupted at a much larger distance from the black hole than a cloud of one solar mass compressed into a volume the size of our solar system. If gas clouds approaching the tidal radius are already in a state of advanced collapse, already far denser than typical molecular clouds, their self-gravity might be strong enough to overcome tidal disruption and complete star formation, even within the forbidden zone. This explanation requires gas to arrive at the tidal radius in a pre-compressed state. Something must have compressed it before it got there. Shockwaves from supernova explosions, collisions between gas streams in the galactic center region, or compression by the magnetic fields threading the central region might accomplish this pre-compression. If the raw material for star formation arrives at the tidal boundary already partially collapsed, the final stages of the collapse might proceed faster than tidal forces can disrupt the cloud. Neither explanation has been confirmed. Both remain speculative in the specific sense that science uses that word not meaning implausible, but meaning not yet tested against sufficient data to be accepted or rejected with confidence. The theoretical work to evaluate these possibilities is ongoing, driven by Webb's detections and informed by the broader data the telescope has gathered about the galactic center environment. The protostellar detections were not Webb's only surprise. The telescope's spectrometers, instruments that spread incoming light into its component wavelengths and measure the intensity at each wavelength with extraordinary precision, revealed the chemical composition of gas throughout galactic center region in more detail than any previous observation. Most of what they found matched expectations. Hot ionized hydrogen glowing at temperatures of 10,000 degrees, carbon monoxide in molecular form, atomic transitions from common elements at predicted intensities. The galactic center confirmed as a hydrogen-dominated environment where the familiar alchemy of stellar birth and death operates, if in an extreme and unusual setting. Then came the water. Webb detected spectral signatures consistent with water vapor at multiple locations within the central few light years of the galaxy. Not water ice locked in dust grains, which is expected and unremarkable in cold regions of space. Water vapor molecules of H2O in gaseous form, intact, present in detectable quantities in an environment where they should not be able to survive. The reason is straightforward. Water molecules are fragile by the standards of interstellar chemistry. The bonds holding hydrogen and oxygen atoms together break when struck by photons carrying sufficient energy, specifically ultraviolet photons. The galactic center is saturated with ultraviolet radiation from the massive young stars crowding the region. A water molecule released into the open gas of the galactic center would on average be destroyed within hours. Not years, not centuries, hours. For water vapor to exist in detectable quantities, it must either be produced continuously at rates exceeding destruction, or it must be protected in shielded environments where ultraviolet radiation cannot reach. The detection is not merely a chemical curiosity. Water is one of the most efficient coolants available in astrophysical gas. When gas containing water molecules is heated by radiation from nearby stars, by shock waves, by the gravitational compression of infall, the excited water molecules can radiate energy away as infrared photons, cooling the gas more effectively than most other molecular species. Cool gas can collapse. Hot gas pressure supported against gravity resists collapse. If water exists near Sagittarius A times in sufficient quantities, it could enable the very gas cooling that allows star formation to proceed in a region where heating processes should keep everything too hot and diffuse to collapse. The connection is suggestive in a way that scientists are careful not to overstate but impossible to ignore. The same regions where Webb detected water vapor overlap at least partially with the regions where protostellar signatures were found. If water is cooling gas in these locations, enabling collapse that would otherwise be suppressed by thermal pressure, then the molecule might be a critical ingredient in the paradox of galactic center star formation. Water may be the reason stars can be born in the shadow of a black hole. The ionized neon was harder to explain. Neon is a noble gas, chemically inert, resistant to forming molecules existing in space, almost exclusively as individual atoms. Stripping an electron from a neon atom requires photons carrying more than 21 electron volts of energy. This places neon ionization firmly in the extreme ultraviolet and soft X-ray regime wavelengths produced primarily by very hot stars with surface temperatures exceeding 30,000 degrees, or by energetic radiation from active galactic nuclei. Ionized neon glowing in a region means something powerful enough to ionize. It is present or was recently present. Webb detected ionized neon emission at locations in the galactic center, where no sufficient ionization source could be identified. The hot stars catalogued in the region, massive O-type and B-type stars producing copious ultraviolet radiation, were mapped precisely by Webb's instruments. Their radiation fields were calculated carefully, accounting for distance and the absorption of photons by intervening gas. At the locations where ionized neon glowed, the calculated radiation field from known stars fell short of the ionization threshold by significant margins. The black hole's current energy output modest, as it is provided insufficient ionizing flux at those distances. Nothing Webb could see was powerful enough to produce the emission Webb was detecting. 3 possibilities presented themselves, and each carries implications that extend far beyond the chemistry of neon. The first involves hidden radiation sources, hot stars, or other energetic objects present in the galactic center region, but undetected by Webb because their emission peaks at wavelengths outside the telescope's observing range, or because they are obscured by local concentrations of dust too dense even for infrared light to penetrate. This explanation is possible but unsatisfying. Webb sees through dust with a thoroughness that has revealed stellar populations invisible to every previous observatory. Hiding an ionizing source powerful enough to produce the observed emission from Webb requires a level of obscuration that seems difficult to arrange without leaving other observable signatures. The second possibility involves cosmic rays, protons, and heavier atomic nuclei accelerated to near light speed by processes near the black hole, streaming outward through the galactic center environment and depositing energy in the gas as they collide with atoms and molecules. The galactic center is one of the most powerful cosmic ray production sites in the Milky Way, and the particle flux in the central region exceeds that of the broader galaxy by substantial factors. Cosmic ray ionization proceeds through different physics than photon ionization, but can produce similar observable effects. If the cosmic ray flux near Sagittarius A times is significantly higher than current estimates, it might account for the ionized neon in regions where photon ionization is insufficient. The third possibility is the most historically resonant. The ionized neon might be a relic, a fossil signature of past activity from Sagittarius A times itself. If the black hole experienced a powerful outburst in the past, the intense radiation from that event could have ionized gas across a wide region of the galactic center. After the outburst faded, the ionized gas would gradually recombine ions, capturing electrons and returning to neutral form, but this process takes time. In regions of sufficiently low density, the recombination timescale can extend to thousands of years. We might be observing the slowly fading afterglow of an ancient X-ray flare gas, still glowing from energy deposited centuries or millennia ago, the echo of an awakening that ended before human civilization learned to write. This third explanation connects to everything we already know about Sagittarius. A. Asterisk's recent history, the X-ray fluorescence of molecular clouds, the evidence for elevated activity a few centuries ago, the Fermi Bubbles, recording a more dramatic outburst millions of years in the past. If ionized neon is a relic, it adds another layer to the stratigraphic record of the black hole's behavior, another line written in glowing atoms across the depth of cosmic time. Webb also revealed with unprecedented clarity the internal structure of the mini-spirals, 3 streams of ionized gas, named the northern arm, the eastern arm, and the western arc flowing towards Sagittarius A, times from distances of several light years. Previous observations had shown these structures as smooth, continuous streams following curved trajectories determined by the black hole's gravity. The gas appeared to flow steadily inward in a pattern that accretion models described as gradual, predictable, and relatively uniform. Webb's resolution dissolved this picture entirely. The mini-spiral arms seen clearly for the first time are not smooth. They are clumpy, containing dense concentrations of gas embedded within the broader streams, moving along trajectories that differ subtly but measurably from the surrounding flow. Individual clumps within the arms measure hundreds of astronomical units across roughly the scale of our solar system, yet contain enough concentrated mass to produce distinct spectral signatures that Webb's instruments could isolate from the surrounding emission. These clumps matter because of what they represent in the physics of black hole feeding. A smooth accretion flow produces relatively steady energy output. Material falls inward, gradually releases gravitational energy at a roughly constant rate, and produces the kind of low-level flickering activity that characterizes Sagittarius A times today. But a clumpy accretion flow is fundamentally different in character. When a dense clump reaches the innermost region of the accretion flow, the zone closest to the event horizon where the release of gravitational energy is most intense, it produces a transient brightening, a flare, an outburst above the baseline that lasts as long as the clump takes to be consumed, then fades as the next quieter interval begins. The clumps Webb detected in the mini-spirals are moving. They are on trajectories that will carry them progressively closer to Sagittarius A times over the coming decades to centuries. Each one represents a potential future flare, a small awakening modest compared to the Fermi bubble events, but measurable, detectable, perhaps bright enough to be visible to the next generation of observatories monitoring the galactic center in real time. The most immediate of these potential feeding events may involve the innermost structure. Webb detected a disk of gas orbiting within approximately 1 light month of Sagittarius A times well inside the orbits of the closest known stars. Material in this disk moves at speeds approaching 10% of the speed of light. It is heated to temperatures exceeding 100 million degrees. It represents the final staging area before matter crosses the event horizon and vanishes from the observable universe forever. 1 light month. The distance light travels in 30 days. At the speed of the fastest spacecraft humanity has ever launched, you would need roughly 6,000 years to cross that distance. To Sagittarius A times, it is the equivalent of food already in the throat, already committed to the swallow. The matter in this innermost disk will fall into the black hole within the next few centuries to millennia. There is no path back for it. The only question is how quickly it falls and how much energy it releases on the way down. Webb has given us for the first time a direct view of this final approach. The geometry and temperature profile of the innermost disk constrain the physical processes governing how angular momentum, the quantity that keeps material in orbit and must be removed for accretion to occur, is transferred outward through the infalling gas. The measurements distinguish between different theoretical models of accretion, eliminating some possibilities and strengthening others. The result is a more precise picture of the mechanism by which Sagittarius A times feeds quiet as that feeding currently is. Everything Webb found in the galactic center pointed toward the same conclusion, approached from different angles expressed through different wavelengths and different physical processes. Sagittarius A times is not a static object presiding over a frozen environment. It is the center of a dynamic churning, constantly evolving ecosystem of gas and stars, where processes are actively underway, star formation proceeding in defiance of theory, chemistry operating in conditions that should prevent it, feeding mechanisms carrying material toward the event horizon on timescales measured in human lifetimes. The monster is not simply sleeping, it is dreaming, and in those dreams the ingredients for its next awakening are quietly, patiently assembling themselves in the darkness at the heart of the Milky Way. 1714. Claude responded, "The starvation of Sagittarius A times is not a mystery of supply. The starvation of Sagittarius A times is not a mystery of supply. The fuel exists. It orbits within reach, flows through the mini-spirals, streams outward, from stellar winds shed by massive stars living their brief, furious lives within the central parsec. If you gathered all the material available within 10 light-years of the black hole and weighed it, you would count tens of thousands of solar masses of gas and dust, enough, if consumed efficiently, to power the black hole at near maximum luminosity for millions of years. The mystery is not where the food is. The mystery is why none of it is being eaten. To understand this, you need to understand something counterintuitive about how black holes consume matter. The process is not simple, gravitational swallowing the way a drain pulls water directly downward. Matter falling toward a black hole carries angular momentum, the quantity that describes rotational motion in the same property that keeps planets in orbit around the Sun and keeps water spinning in a whirlpool long after the drain has opened. Angular momentum is conserved. It cannot simply disappear, and because infalling matter carries angular momentum, it cannot fall straight inward. It must spiral, trading potential energy for kinetic energy, while gradually losing angular momentum through friction and other processes to neighboring material. This spiraling produces what astronomers call an accretion disk, a flattened structure of orbiting gas extending from near the event horizon outward to wherever the infalling material originates. In active galactic nuclei in quasars blazing across billions of light-years, this disk is thin, dense, and extraordinarily efficient. Material cools as it loses energy, settling into a compact configuration close to the black hole's equatorial plane. The cooling allows the disk to remain thin. The thinness concentrates the gas, enabling efficient transfer of angular momentum outward through the disk. Material spirals steadily inward, releasing gravitational energy as radiation at roughly 10% efficiency, meaning that for every unit of mass that falls into the black hole, 10% of its rest mass energy escapes as light. This is the most efficient energy conversion process in nature, exceeding nuclear fusion by a factor of 10. Sagittarius A times operates in a completely different regime. The gas approaching the event horizon is not cool. It is not dense. It does not form a thin disk. Instead, it exists as a hot, puffed-up dilute cloud of plasma, threaded with magnetic fields and turbulent motions, a structure so different from the efficient thin disks of active quasars that it requires an entirely separate theoretical framework to describe. This framework is called advection-dominated accretion flow, and it is the reason Sagittarius A times sits in near darkness despite being surrounded by potential fuel. The mechanism works as follows. Gas falling towards Sagittarius A times does release gravitational energy as it compresses. That energy heats the gas. In a dense accretion disk, the heated gas radiates this energy away quickly. Photons escape the disk on time scales short enough that the gas cools before pressure builds significantly. The cooling keeps the disk thin and dense, enabling efficient further infall. But in a dilute, low-density flow like that surrounding Sagittarius A*, the situation reverses. The gas is too thin for photons to escape efficiently. Radiation is trapped within the flow rather than escaping outward. The trapped energy keeps the gas hot, and hot gas has pressure. That pressure resists further compression. The accretion flow puffs up into a roughly spherical turbulent structure, rather than settling into a thin disk. Most of the gravitational energy released during infall is not radiated away. It is advected, carried inward with the falling gas swallowed by the black hole as thermal energy, rather than escaping as light. Hence the name advection-dominated. The black hole is consuming energy along with mass, but producing almost no observable radiation in the process. It is feeding in the dark, gaining mass and energy with extraordinary inefficiency from the perspective of an outside observer, and producing only a tiny fraction of the luminosity that the same mass accretion would generate in a thin disk system. Webb spectroscopic observations of the innermost gas near Sagittarius A times provided the first detailed empirical measurements of this advection-dominated flow. The temperature profiles, density distributions, and velocity structures measured by the telescope constrain the theoretical models in ways that ground-based observations never could. What the data revealed was a flow even more complex and turbulent than the models had assumed. The theoretical framework that physicists had built to describe advection-dominated accretion is largely correct in its broad strokes. but the details are messier, more variable, more sensitive to initial conditions than the elegant mathematical descriptions suggested. The turbulence within the flow creates constant variability. Dense pockets of gas form and dissolve on timescales of hours. Magnetic field lines wind and twist through the infalling material, occasionally snapping into new configurations and releasing stored energy in sudden bursts. Material that should spiral smoothly inward instead follows chaotic paths, sometimes flung outward before eventually falling back, sometimes finding efficient inward channels that carry it to the event horizon faster than average. The result is the flickering, erratic behavior that characterizes Sagittarius A times in modern observations, small flares erupting several times daily, varying unpredictably in intensity and duration, superimposed on a baseline that itself varies on longer timescales. These daily flares are not trivial events measured against any terrestrial standard. A typical flare from Sagittarius A times releases over the course of an hour more energy than our Sun produces in an entire year. The flare brightens the black hole by factors of 10 to 100 across infrared and X-ray wavelengths simultaneously, then fades back to baseline as the triggering event, most likely a magnetic reconnection episode, where wound magnetic field lines snap into a new configuration and release their stored energy suddenly exhausts itself. Webb captured several such flares during its Galactic Center monitoring campaign, watching their spectral evolution with a precision no previous observatory had achieved. The flare spectra revealed that two distinct physical processes operate simultaneously during these events. Hot thermal emission from gas heated to temperatures exceeding 100 million degrees contributes a broad continuum of radiation, but superimposed on this thermal component is non-thermal emission radiation produced not by the random thermal motions of heated particles, but by electrons moving at significant fractions of light speed, spiraling through magnetic fields and radiating through a process called synchrotron emission. The non-thermal component requires particle acceleration to relativistic speeds, which in turn requires the magnetic reconnection mechanism. The simultaneous presence of both components in Webb's flare spectra confirmed that galactic center flares involve both thermal heating and relativistic particle acceleration occurring together during each event. Understanding the daily flares matters for understanding what triggers larger awakenings. If small flares result from magnetic reconnection episodes in the innermost accretion flow, larger outbursts might result from the same mechanism operating at greater scale. Larger regions of wound magnetic field, larger reconnection events, larger releases of stored energy. Or they might result from something qualitatively different. Discrete events that suddenly dump large quantities of material into the accretion flow, overwhelming the advection-dominated regime and driving the system temporarily towards something more like the efficient thin disk accretion of an active quasar. The most dramatic version of such a discrete event is a tidal disruption, when a star wanders within the tidal radius of Sagittarius A times the gravitational gradient tears it apart. The debris forms a long stream of gas, roughly half of which becomes bound to the black hole and begins spiraling inward. As this material accumulates and falls toward the event horizon, it releases gravitational energy at rates millions of times higher than the current background accretion. The black hole's luminosity increases correspondingly, potentially by factors of millions or even billions, persisting for months to years before the stellar debris is exhausted. Tidal disruption events are observed in distant galaxies at rates of roughly 1 per 100,000 years per galaxy. Given this rate, the Milky Way should experience such an event within the next few 100,000 years on average. Whether the most recent such event occurred thousands of years ago, tens of thousands of years ago, or is still in our near future, cannot be determined from current data. What we can say is that the X-ray fluorescence evidence for elevated activity a few centuries ago is not obviously consistent with a full stellar tidal disruption, which would have been far more luminous. The recent activity may represent a smaller event, a dense gas cloud disrupted rather than a star, or a partial tidal disruption where the star survived but lost a fraction of its mass to the black hole. The story of one specific object illuminates both the promise and the complexity of predicting such events. In 2011, astronomers monitoring the galactic center detected what appeared to be a dense gas cloud on a trajectory that would carry it within 200 astronomical units of Sagittarius A, times well inside the tidal radius for a pure gas structure. The object was designated G2. Its orbit was calculated precisely from multiple years of observations. The closest approach was predicted for the spring of 2014, and the astronomical community prepared to watch what many expected would be a dramatic feeding event. Observatories around the world scheduled time on their instruments to monitor the encounter. Theoretical models predicted that G2 would be stretched into a long, thin stream of gas as it approached the black hole, with roughly half the material falling inward to produce a brightening lasting months to years. The event was compared in the press and in scientific discussions to a comet approaching the Sun, except the comet was a gas cloud containing roughly 3 Earth masses of material, and the Sun was a 4 million solar mass black hole. G2 reached closest approach in 2014. The fireworks did not occur. The cloud passed within the predicted distance of Sagittarius A times and emerged from the encounter, stretched, elongated, partially disrupted, but intact. Its core survived. The expected brightening, the months-long elevated emission, the dramatic feeding event that scores of observatories had prepared to witness, none of it happened. Sagittarius A times produced some modest enhancement in its small daily flares during the period of closest approach, but nothing approaching the predicted outburst. The monster had the opportunity and chose not to eat. Or more precisely, the object that astronomers had assumed would be consumed proved more resilient than the models assumed. The survival of G2 taught 2 important lessons. The first concerns the nature of the object itself. Pure gas clouds with the mass and size of G2 should not survive tidal disruption at such close range. The most likely explanation for its survival is that G2 contains a central stellar core, a star, embedded within a dusty, gas-rich envelope whose self-gravity held the object together through the encounter. The star's gravity provided structural integrity that a pure gas cloud lacks. G2 might be a young stellar object still embedded in its birth material, or a stellar merger product surrounded by gas shed during the collision. Its exact nature remains debated, but its survival definitively argues against a pure gas composition. The second lesson concerns the difficulty of predicting when Sagittarius A times will receive significant feeding events. The galactic center harbors numerous objects on trajectories that bring them periodically close to the black hole. Some of these objects are gas clouds that might be disrupted and consumed. Others contain stellar cores that will survive their encounters intact. Distinguishing between these categories requires observations detailed enough to detect the stellar component within the dusty envelope, exactly the kind of observation Webb was designed to make. Webb identified several objects in the galactic center region that had not been catalogued by previous observatories on trajectories that will bring them within varying distances of Sagittarius A times over the coming decades, centuries. The telescope's ability to resolve stellar cores within dusty envelopes, the capability that would have identified G2's nature immediately had Webb been available in 2011, allows astronomers to assess which of these objects represents genuine feeding threats and which will survive. Their closest approach is intact. Among Webb's more tantalizing discoveries in the galactic center region were several sources that defied straightforward classification. These objects appeared as point sources in infrared compact enough that they could not be resolved into extended structures, but with properties inconsistent with any normal stellar category. Their colors in different infrared wavelengths did not match main sequence stars, giant stars, or any standard stellar evolutionary stage. Their luminosities placed them in ranges occupied by unusually massive objects. Their apparent motions across the sky, measured by comparing Webb's positions to earlier observations from ground-based telescopes, were consistent with orbital velocities around Sagittarius A times expected for massive compact objects. The cautious interpretation, the one that responsible scientists offer when faced with unusual detections, is that these objects require further observation before their nature can be determined. They might be unusual stars with properties outside the normal range. They might be binary star systems appearing point-like at the galactic center distance. They might be young stellar objects still embedded in dense, warm dust that alters their spectral appearance. But the less cautious interpretation, the one that theoretical frameworks for black hole evolution would predict, and that the observed properties are at least consistent with, is that some of these objects might be intermediate mass black holes, objects with masses between roughly 100 and 100,000 solar masses, too small to be supermassive, but too large to have formed from the death of a single star. Objects that represent, in the hierarchy of black hole formation and growth, the missing link between stellar mass black holes produced by supernova explosions and the supermassive behemoths ruling galactic centers. Intermediate mass black holes are among the most sought-after objects in modern astrophysics, precisely because they are so difficult to find. They emit no light of their own. They are too small to significantly influence the motions of stars, except at very close range. They do not produce the characteristic radio or X-ray signatures of accreting supermassive black holes because they rarely encounter enough material to feed significantly. They are dark, compact, and essentially invisible to indirect detection methods that work for their larger and smaller cousins. Yet they should exist. Theory demands them. The same processes that produce stellar mass black holes from dying stars should occasionally produce black holes at the upper end of the stellar mass range, objects of hundreds of solar masses that might then grow through mergers or accretion toward the intermediate mass regime. Dense star clusters experiencing runaway stellar collisions should be capable of building objects of thousands of solar masses before the central condensation collapses into a black hole. Dwarf galaxies consumed by larger galaxies should deposit their central black holes into the host galaxy's nucleus, where they then sink inward through dynamical friction. Dynamical friction is the process by which a massive object moving through a sea of lighter particles loses energy through gravitational interactions with those particles. Each star that passes near an intermediate mass black hole receives a tiny gravitational tug that marginally alters its orbit. The cumulative effect of millions of such interactions transfers orbital energy from the black hole to the stellar population, causing the black hole to spiral gradually toward lower energy orbits closer to the galactic center. The timescale for this spiral depends on the black hole's mass and the density of the stellar environment through which it moves. In the galactic center region, where stellar densities are among the highest in the Milky Way, dynamical friction operates efficiently enough to deliver intermediate mass black holes to the vicinity of Sagittarius A, times within hundreds of millions of years. If Webb has indeed detected intermediate mass black holes orbiting within the central parsec of the Milky Way, their presence suggests that the galactic center is actively engaged in the process of hierarchical black hole assembly, smaller black holes spiraling inward over time eventually, merging with Sagittarius A times and adding their mass to the central object. Each merger would represent a gravitational wave event of a kind that no current detector can observe, falling in the frequency gap between ground-based instruments like LIGO and the space-based observatories of the future. But the merger rate implied by Webb's potential detections would produce a gravitational wave background at those frequencies that future missions like LISA, the Laser Interferometer Space Antenna, planned for launch in the 2030s, should be able to detect statistically, if not resolve as individual events. The question of when Sagittarius A times will next experience a significant awakening thus involves multiple timescales operating simultaneously. On the scale of decades, the dense gas clumps Webb detected within the mini-spirals will approach closer to the event horizon, potentially producing enhanced flaring activity detectable by the observatories that will follow Webb. On the scale of centuries to millennia, the material in the innermost disk will be consumed, and new material from the mini-spirals will need to replace it, a process whose efficiency determines whether the next few centuries see more or less activity than the current baseline. On the scale of tens of thousands to millions of years, a stellar tidal disruption event is statistically likely, potentially producing a dramatic brightening that would be visible across the galaxy. On the scale of hundreds of millions of years, intermediate mass black holes spiraling inward through dynamical friction will eventually reach Sagittarius A times and merge, producing the most powerful gravitational wave events our galactic neighborhood will ever generate. And threading through all of these timescales, operating continuously and invisibly, is the slow assembly of conditions that preceded the Fermi bubble events. The gradual accumulation of dense gas near the galactic center, the building of whatever triggered the last major active phase, a process whose timescale we do not know and whose next occurrence we cannot predict. The silence of Sagittarius A times is real, but it is the silence of potential, not of permanence. Every measurement Webb has made in the galactic center region confirms that the ingredients for awakening are present. The gas is there. The clumps are there. The infalling material is there. The magnetic fields that could trigger reconnection events at larger scales than the daily flares are there. The stars on orbits that will eventually carry some of them within the tidal radius are there, following their 16-year or 100-year or 1,000-year paths around the gravitational monster at the center of our galaxy. The only question, the question that no observation can yet answer, that no theory can yet resolve, is which of these processes will reach its critical threshold first, and what will happen to the galaxy around it when it does. The distance from Earth to Sagittarius A times is 26000 light-years. That number is large enough to feel abstract, to function as a kind of conceptual shield between the reader and the object being described. 26,000 light-years. The words carry a sense of vast, comfortable remove. Whatever happens there, the implicit assumption runs, happens far enough away that it cannot reach us in any meaningful sense. That assumption requires careful examination, because distance in the context of an awakening supermassive black hole is not simply a measure of separation. It is a measure of delay, and delay over the timescales involved in galactic center physics is a more complicated concept than it first appears. Every photon Webb has collected from the galactic center left its source 26000 years ago. The protostellar signatures, the ionized neon, the clumps within the mini-spirals, the innermost disk of superheated gas approaching the event horizon, all of it is history. Ancient history by human standards, though recent by the standards of a galaxy 13 billion years old. When those photons departed, the galactic center, the last great ice age, was in its final stages. Glaciers still covered much of northern Europe and North America. Humans were painting animals on cave walls in what would become France and Spain. Agriculture did not exist. Writing did not exist. Everything we call civilization, every city, every language, every technology, every war, every philosophical tradition, every piece of music ever composed, all of it unfolded during the time it took that light to cross the distance between the galactic center and Webb's golden mirrors. This means we cannot know the current state of Sagittarius A asterisk. We can only know its state 26000 years ago and extrapolate from theory. The black hole might have woken already. A tidal disruption event might have occurred 10,000 years ago, flooding the galactic center with X-rays and ultraviolet radiation, driving powerful outflows through the surrounding gas, producing changes in the local environment that are still propagating outward through the Milky Way. That information is racing toward us at the speed of light, and we will not receive it for another 16,000 years. Alternatively, the black hole might remain in its current quiet state for millions of years to come. We are observing history always. The present state of the galactic center is in the strictest physical sense inaccessible to us. What we can do is reason carefully about what an awakening would mean, using the physics established by Webb's observations and decades of prior study to understand the consequences at different distances and different time scales. Begin at Earth. The 26000 light-year distance provides substantial natural shielding, but it is not absolute. An awakening Sagittarius A times would not leave our planet untouched. The nature and severity of the effects depend critically on what kind of awakening occurs. A modest activation, comparable to the activity implied by the X-ray fluorescence evidence from a few centuries ago, millions of times, more luminous than today, but still far below quasar levels, would produce effects detectable by astronomers, but not directly dangerous to life on Earth's surface. The most immediately visible consequence would be a change in the night sky. The galactic center region would brighten across every wavelength. The intervening dust, which currently renders the galactic center invisible to optical telescopes, absorbs different wavelengths with different efficiencies. Visible light is almost completely blocked. Infrared light penetrates with only modest attenuation. X-rays at sufficiently high energies can pass through the dust with relatively little absorption. A significantly more active Sagittarius A times would produce enough infrared emission to brighten the galactic center region measurably, even through the dust. In the direction of Sagittarius on a clear, dark night, human eyes might detect a subtle enhancement in the diffuse glow of the Milky Way. More significantly, X-ray and gamma-ray observatories would see dramatic changes. The galactic center, currently a moderately interesting X-ray source amid many others in the sky, would become the most luminous X-ray object visible from Earth by an enormous margin. Space-based X-ray telescopes would need to reduce their sensitivity or risk saturating their detectors. The scientific data flowing from such observatories would represent an unprecedented opportunity to study black hole physics in the highest possible detail in our own galactic backyard, with instruments that decades of technological development had made extraordinarily capable. The radiation reaching Earth's surface from an activated Sagittarius A times would be attenuated by 26,000 light-years of interstellar medium and then by Earth's own atmosphere. High-energy gamma rays would be absorbed in the upper atmosphere, producing air showers of secondary particles that detectors on the ground could measure. X-rays would be blocked well above the surface. The increasing cosmic ray flux, high-energy particles accelerated near the black hole and propagating outward through the galaxy along magnetic field lines would be more modest, arriving gradually over thousands of years as the particles diffuse through the interstellar medium rather than traveling in straight lines at light speed, on time scales of centuries to millennia. Following a significant awakening, the cosmic ray flux reaching the inner solar system might increase by measurable amounts. Cosmic rays interact with Earth's atmosphere, producing a cascade of secondary particles, including muons that penetrate to the surface. They contribute to background radiation levels, influence atmospheric chemistry in minor ways, and affect the rate of certain types of DNA damage in living organisms. A moderate increase in cosmic ray flux would not produce biological catastrophe, the levels involved in a modest galactic center activation would remain well within the range that life on Earth has experienced throughout its history, driven by natural variation in the sun's activity and in the local interstellar environment. For modern technology, cosmic rays present a different kind of concern. High-energy particles striking semiconductor devices can flip individual bits in computer memory, a phenomenon called a single-event upset. Critical systems in aircraft, spacecraft, medical devices, and financial infrastructure already contend with this problem through error-correcting codes and radiation-hardened designs. A significant increase in cosmic ray flux would raise the frequency of such events, requiring more robust protection in sensitive electronics. This is an engineering challenge, not an existential threat, but it illustrates that the effects of galactic center activity are not purely astronomical curiosities for Earth's technological civilization. The effects grow dramatically as you move closer to the galactic center. At 10,000 light-years from Sagittarius A, times a distance that places a hypothetical observer still well within the Milky Way's disk, among billions of ordinary stars orbiting the galactic center. The radiation environment during a major awakening would be qualitatively different from anything Earth experiences. The dust absorption that protects our planet would be less effective at closer range. The radiation flux falling off with the square of distance would be orders of magnitude more intense. A planet orbiting a sun-like star at 10,000 light-years from the galactic center during a full quasar-level activation of Sagittarius A times would receive X-ray and ultraviolet irradiation far exceeding what Earth's surface experiences from our own sun. Planetary atmospheres provide the critical shield. Earth's atmosphere absorbs essentially all solar X-rays and extreme ultraviolet radiation before it reaches the surface. A thick nitrogen-oxygen atmosphere similar to Earth's would similarly absorb galactic center radiation during a modest awakening. But the efficiency of this absorption depends on the atmospheric composition and column density. Over extended periods of intense irradiation, high-energy photons can drive photochemical reactions in the upper atmosphere, potentially affecting the ozone layer and altering surface UV levels, even when direct penetration is limited. At distances of a few thousand light-years from Sagittarius A times the inner reaches of the galactic disk, a major awakening would present serious challenges to any biosphere. The radiation flux at these distances during quasar-level activity would exceed anything Earth has experienced from our Sun by large factors. Planetary atmospheres would be stressed by the energy input. Atmospheric escape, the process by which energetic radiation heats upper atmospheric layers until gas molecules achieve escape velocity and a loss to space, would accelerate. Planets that had spent billions of years building habitable atmospheres might lose them on geological timescales during an extended active phase of the central black hole. The inner galaxy within a few thousand light-years of the galactic center may be genuinely hostile to the development and persistence of complex life. Not because individual stellar systems are inhospitable in the way that, say, stars near a pulsar or an X-ray binary are inhospitable to nearby planets, but because the long-term radiation environment averaged over the billion-year timescales required for complex life to evolve includes periodic exposures to elevated galactic center activity that would interrupt biological continuity. Each major awakening of Sagittarius A times would represent a reset event for any biosphere within the danger zone, potentially sterilizing planetary surfaces and requiring the re-evolution of complex life from surviving simpler organisms. This consideration connects to one of the deeper questions about why Earth finds itself where it does in the Milky Way. Our solar system occupies a position in one of the galaxy's outer spiral arms, roughly halfway between the galactic center and the outer edge of the disk. This location is not the galactic equivalent of prime real estate. It is a quiet suburb far from the dense stellar populations and energetic environments of the inner galaxy. For most of human history, this peripheral location seemed simply a fact of cosmic geography. We are where we are, and asking why serves no obvious purpose. But the emerging picture of galactic center activity suggests that our location might be relevant to our existence in a more direct way. The concept has a name in the astrobiological literature, the galactic habitable zone. Just as planets orbit their stars within a range of distances, neither so close that they are scorched by radiation and stripped of atmosphere, nor so far that they are frozen solid, perhaps solar systems within a galaxy occupy a range of distances from the galactic center within which complex life is more likely to develop and persist. Too close to the center and the radiation environment is too harsh, the stellar density too high, the frequency of disruptive gravitational encounters too great. Too far from the center and the stellar metallicity, the abundance of elements heavier than hydrogen and helium required to build rocky planets, and the complex chemistry of life becomes too low. Earth sits in a region of the galaxy where metallicity is adequate for planet formation, and where the galactic center's periodic activity represents a distant background hazard rather than a recurring existential threat. Whether this is coincidence or selection, whether the existence of observers necessarily implies a location protected from the worst effects of galactic center activity, is a question. Anthropic reasoning about why we find ourselves in the particular universe we inhabit. What is certain is this: if technological civilizations exist closer to the galactic center than we do, and statistical arguments about the sheer number of potentially habitable planets in the inner galaxy suggest they might or might have, at some point in the galaxy's history, those civilizations would have a relationship with Sagittarius A times that is fundamentally different from ours. For them, the black hole would not be a distant academic subject, a fascinating astronomical object studied through telescopes pointed across thousands of light years. It would be a presence, a dominant feature of their sky, and their long-term survival planning. A civilization at 5,000 light-years from the galactic center, sufficiently advanced to understand astrophysics and sufficiently long-lived to observe the galactic center across millennia, would have watched Sagittarius A** cycle through quiet and active phases repeatedly during their remiss history. They would have experienced the radiation environment change measurably within single lifetimes during active phases. They would have developed, if they survived long enough, technologies to monitor and respond to galactic center activity warning systems to detect the earliest signs of awakening shielding to protect their population during elevated radiation periods, or the capability to relocate populations to safer distances when activity exceeded manageable levels. For such a civilization, the Fermi bubbles would not be abstract structures detected by gamma-ray telescopes. They would be visible features of the sky extending above and below the galactic plane in directions they could point to on a clear night. The X-ray fluorescence of molecular clouds reflecting ancient outbursts from Sagittarius A times would be observable directly from their planetary surface, illuminating their astronomical history with evidence of cataclysms their distant ancestors survived. The relationship between an inner galaxy civilization and its central black hole would be intimate in a way that our own relationship with Sagittarius A times simply is not. Whether such civilizations exist or have existed in the Milky Way's inner regions is unknown. What the combination of galactic habitable zone arguments and galactic center activity history suggests is that the inner galaxy may have experienced periodic sterilization events that reset the clock for complex life development. Each major activation of Sagittarius A times would represent a biological catastrophe for unshielded life at close range, followed by a period of recovery during the subsequent quiet phase. The development of complex technological civilization might require the kind of extended, uninterrupted quiet that the galactic center's periodic awakenings have difficulty providing in the inner Milky Way. Our own civilization developed during an exceptionally quiet period in galactic center activity. The Fermi bubbles suggest major activity ended a few million years ago. The X-ray fluorescence implies significantly elevated but not catastrophic activity a few centuries ago. The current period is about as quiet as the galactic center gets. Whether this quiet contributed to the conditions that allowed complex life to flourish on Earth, whether billions of years of relative galactic calm at our distance were a necessary prerequisite for the evolutionary history that produced us, is a question that cannot be answered definitively but deserves serious consideration. Now extend the time scale further. Not centuries, not millennia, not millions of years, billions. In approximately 4 to 5 billion years, the Milky Way will collide with its nearest large neighbor, the Andromeda Galaxy. This merger is not speculative. The trajectory and velocity of Andromeda toward the Milky Way have been measured precisely enough that the collision is essentially certain. The two galaxies are currently approaching each other at roughly 70 miles per second. At this rate, the first close encounter will occur in about 4 billion years, with the galaxies passing through each other and then pulled back by mutual gravity, merging completely over the following billion years or so. The collision will not destroy individual stars. The distances between stars are so vast, even in dense galactic environments, that actual stellar collisions during a galactic merger are extraordinarily rare. Our Sun will survive the merger, though its orbit around the new combined center of mass will be dramatically altered as gravitational perturbations from Andromeda's stars and dark matter reshape the potential well that currently governs the Milky Way's dynamics. Earth will survive as well, assuming no close stellar encounters perturb the solar system's inner planets during the billions of years of dynamical chaos that galaxy mergers produce. What will not survive, unchanged, is the galactic center environment. Andromeda harbors its own supermassive black hole, designated M31 times, with a mass of roughly 100 million solar masses, approximately 25 times more massive than Sagittarius A*. When the two galaxies merge, both black holes will sink toward the common center of mass through the same dynamical friction that causes intermediate mass black holes to spiral inward in the current Milky Way. The in-spiral will take hundreds of millions of years, with the two black holes orbiting each other in an ever-tightening gravitational embrace. During this in-spiral, both black holes will be surrounded by gas and stars from both merged galaxies. The chaotic conditions of a galaxy merger drive gas toward galactic centers with far greater efficiency than the quiet, settled dynamics of an undisturbed spiral galaxy. Enormous quantities of fuel will be funneled toward the central region of the merged system. The probability that one or both black holes will experience a major feeding event during or immediately following the merger is substantially higher than the probability during the current quiet epoch. The merged system might shine as a quasar, Sagittarius A times or M31 times, or both fed by the bounty of colliding gas from two spiral galaxies, might activate at luminosities approaching or exceeding their Eddington limits. The central region of the merged galaxy would blaze with energy output dwarfing anything in our current cosmic neighborhood. For any civilization surviving the merger in a location distant enough from the galactic center to avoid sterilization, the night sky would be transformed. The new galactic center, no longer hidden behind dust in the direction of Sagittarius, but repositioned relative to the merged stellar populations, would outshine everything else. Visible, a point of brilliant light, announcing the feeding of a black hole that has consumed the fuel of two colliding galaxies. The eventual merger of the two black holes themselves would be the most powerful gravitational wave event our local universe will ever produce. When two black holes of these masses spiral together to within a few gravitational radii and begin their final plunge, the space-time distortion propagates outward as gravitational waves carrying energy exceeding the combined luminosity of all stars in both merged galaxies at the moment of coalescence. A space-time ripple crossing the universe, announcing to any sufficiently sensitive detector in any sufficiently advanced civilization anywhere within billions of light years that two monsters have become one. The merged black hole would weigh over 100 million solar masses, combining the masses of both progenitors minus the few percent radiated away as gravitational waves during the merger. This new object would inherit the combined gas and stellar populations of both galaxies, presiding over what would by then be a single large elliptical galaxy. The organized spiral arms of both predecessors long since dissolved into the random stellar orbits that characterize the aftermath of galactic mergers. Earth in its current form will not witness any of this. The Sun will exhaust its hydrogen fuel in approximately 5 billion years and expand into a red giant engulfing the inner planets. Long before the actual expansion, the increasing solar luminosity will push Earth's surface temperature beyond the range compatible with liquid water, ending the conditions that have supported life here for billions of years. Whatever descendants of human civilization might observe, the galactic merger will do so from wherever they have relocated other stellar systems, artificial habitats, or environments we cannot currently imagine after an interval of time, longer than the entire history of complex life on Earth, up to the present moment. The galactic merger is not an ending, it is a transformation. The Milky Way and Andromeda will cease to exist as separate entities and become something new, a larger, more massive system with a more powerful central black hole, a different stellar population, a transformed relationship between its center and its outskirts. The history of our galaxy, including the history of Sagittarius A times and everything Webb has revealed about its sleeping depths and its ancient violence, will be subsumed into a longer history still unfolding. We exist at a specific moment in this unfolding, after the last major activation of the galactic center's black hole, before the next significant awakening before the galactic merger that will reshape everything. A quiet interval between storms of cosmic scale. The calm at the center of the Milky Way is temporary. It has been temporary for the entire history of our galaxy, punctuated by awakenings large and small, recorded in glowing clouds and enormous bubble structures that persist long after the events that created them. The silence, in other words, is borrowed time, and borrowed time, however generous its duration, always ends. 1719, Claude responded. There is a question that sits underneath everything we have examined, unspoken but present in every observation, every measurement, every theoretical framework. There is a question that sits underneath everything we have examined, unspoken but present in every observation, every measurement, every theoretical framework constructed to explain what Webb found when it looked toward the heart of the Milky Way. It is not a scientific question in the narrow sense. It does not have an answer expressible in equations or confirmed by data, but it is the question that gives all of the data its weight, that transforms a collection of spectroscopic measurements and infrared images into something that matters beyond the professional concerns of astrophysicists. The question is this: what does it mean that we are here at this distance, at this moment, capable of asking? Consider the chain of contingencies that produced this situation. The Milky Way formed from the gravitational collapse of primordial gas roughly 13 billion years ago. Within the first billion years, its central black hole, Sagittarius A, times the object whose silence and history and potential awakening we have spent this entire journey examining, grew through accretion and mergers to its current 4 million solar masses. During the active phases of that growth, the galactic center blazed with energies that would have sterilized any biosphere within thousands of light years. The inner galaxy, for much of the galaxy's early history, was not a place where complex life could develop and persist. Our sun formed approximately 4.6 billion years ago, in the outer reaches of one of the galaxy's spiral arms from a cloud of gas and dust, enriched by billions of years of stellar nucleosynthesis, the process by which successive generations of stars fused hydrogen into heavier elements, lived their lives, and then scattered those elements through supernova explosions into the interstellar medium. Every atom of carbon in your body was forged in the interior of a star that died before our sun was born. Every atom of oxygen you breathe was produced by nuclear reactions in stellar cores scattered across the Milky Way over billions of years. The iron in your blood was created in the catastrophic death throes of stars, far more massive than our sun, in supernova explosions so violent they briefly outshone entire galaxies. Some of that iron, some of those carbon atoms, some of that oxygen, some fraction of the material that eventually became you, was processed through the extreme environment of the galactic center region itself. Stars near Sagittarius A times live brief, furious lives and die as supernovae, scattering their enriched contents into the galactic winds that Webb detected flowing outward from the central parsec. Those winds carry heavy elements away from the galactic center, dispersing them through the broader galaxy, where they eventually mix with the interstellar medium and contribute to the formation of new stellar systems. The atoms forged near the black hole traveled outward for millions of years, mixed with material from countless other sources, and eventually participated in the chemistry of a molecular cloud that collapsed to form our solar system. You are, in a real and non-metaphorical sense, made partly of material that was processed in the vicinity of Sagittarius A*. The connection between the monster at the center of the Milky Way and the observer reading these words is not abstract. It is written in the atomic composition of your body, in the specific isotopic ratios of elements that encode the nuclear history of the material from which you are built. The galactic center shaped your chemistry before your planet existed. And now, you are looking back. This is the thing that should produce genuine awe, not the performed variety that public science communication sometimes reaches for, but the real thing, the sudden vertiginous recognition that the universe has arranged itself into a configuration where matter can contemplate its own origin. The carbon atoms in your brain conducting the electrochemical processes that constitute thought were produced by stellar fusion and scattered by stellar death, and eventually assembled by billions of years of chemistry into a structure capable of wondering about the process that created them. The universe looking at itself, the galaxy examining its own center through instruments built by beings who are themselves products of galactic chemistry. Webb's observations gave us for the first time a clear view of that center, not through veils of dust that obscured everything but the coarsest features, not through radio wavelengths that revealed only the large-scale structure, but in sharp, detailed, chemically specific infrared light that showed individual stars, individual gas clumps, individual signatures of molecules and atoms distributed across the most extreme environment our galaxy contains. The telescope's golden mirrors gold because gold reflects infrared light with extraordinary efficiency. Gold that was itself produced in the violent collisions of neutron stars billions of years before our sun formed, collected photons that had spent 26,000 years crossing the galaxy, and assembled them into images that human minds could examine. What those images showed was not what anyone predicted. Theory said the galactic center should be relatively simple, relatively settled, relatively well understood after decades of observation. The observations said otherwise. Stars forming where stars cannot form, water existing where water cannot exist, ionized gas glowing from energy sources that current physics cannot fully account for, a quiet black hole whose silence is inconsistent with its history, and whose environment is inconsistent with the theory developed to describe it. The inconsistencies are not failures, they are invitations. Every place where observation contradicts prediction is a place where our understanding of the universe is incomplete, and therefore a place where genuine discovery remains possible. The history of physics is a history of exactly such moments. The ultraviolet catastrophe that classical thermodynamics could not explain, and quantum mechanics resolved, the precession of Mercury's orbit that Newtonian gravity could not account for, and general relativity described perfectly the accelerating expansion of the universe that no one predicted and dark energy was invoked to explain. Each apparent failure of theory opened a door to a deeper understanding of how reality operates. The galactic center anomalies Webb revealed are doors of this kind. The protostellar detections in the Forbidden Zone are an invitation to understand star formation in extreme gravitational environments in ways that will ultimately illuminate star formation everywhere. The water vapor surviving in conditions that should destroy it is an invitation to understand interstellar chemistry in radiation fields more intense than anything studied in laboratory conditions. The ionized neon without apparent ionization sources is an invitation to understand the energetic history of Sagittarius A times-on-time scales that bridge the gap between the recent X-ray fluorescence record and the older Fermi Bubble evidence. Each door leads not to simpler rooms but to larger ones with more doors. This is the nature of scientific inquiry at its most productive, not the accumulation of answers that close questions, but the development of understanding deep enough to formulate better questions than were previously possible. Before Webb, astronomers could ask whether stars existed near Sagittarius A*. After Webb, they can ask how those stars form in defiance of tidal forces, which physical mechanisms provide the necessary protection, and what this tells us about star formation in the extreme environments surrounding supermassive black holes throughout the universe. The question has become richer. The inquiry has deepened. The territory of the unknown has not shrunk. It has expanded into a more precisely mapped landscape where the edges of knowledge are clearer and the paths forward more visible. The silence of Sagittarius A times will not last forever. This is not speculation. It is the most robust conclusion available from everything observed, measured, and theorized about the galactic center. The black hole has woken before. The scars of its previous awakenings are visible across tens of thousands of light years of glowing gas and energetic particles. The ingredients for future awakenings are assembling themselves in the darkness of the galactic center. Dense gas clumps spiraling through the mini-spirals toward the innermost accretion flow stars, tracing orbital paths that will eventually bring some of them within reach of tidal disruption. Intermediate mass black holes spiraling inward through the stellar population on timescales of hundreds of millions of years. When the awakening comes, whether in centuries or millennia or millions of years, it will write itself into the galaxy in the same way previous awakenings have, in the fluorescence of molecular clouds preserving the X-ray echo of the event, in the slow expansion of heated gas driven outward from the central region, in the gradual increase of cosmic ray flux, propagating through the galactic magnetic field, in whatever structures form from the energy released, structures that future observers, beings we cannot imagine using, instruments that would be as incomprehensible to us as Webb would be to Jansky, standing beside his merry-go-round in 1932, will examine and catalogue and attempt to explain. Those future observers will look back at the current period of galactic center, quiet the way we look back at the ice ages, as a specific environmental condition now ended that shaped the world in which their civilization developed. They will know from the isotopic record of their own bodies and their own planets that they are products of the same stellar chemistry that produced us. They will look toward where the galactic center sits in their sky and see evidence of the awakening that our era could only anticipate. What they will not see, cannot see, is this moment. This particular configuration of awareness and curiosity and wonder, assembled from galactic chemistry on a small planet, orbiting an ordinary star in the outer reaches of a spiral galaxy, looking outward and inward, simultaneously outward, toward the center of the galaxy and inward toward the implications of what is found there. This moment is unrepeatable, not because it is precious in some sentimental sense, though perhaps it is that too, but because the specific combination of conditions that produced it, the quiet galactic center, the particular evolutionary history of life on this planet, the specific technological development that made Webb possible, will not recur in precisely this form. The photons Webb collected from Sagittarius A times carried information about the galactic center as it existed 260,000 years ago. They crossed the galaxy at the speed of light, the fundamental speed limit of the universe, and arrived at Webb's detectors to be recorded and analyzed and interpreted by minds that had no existence when those photons departed their source. The communication between the galactic center and human understanding required 260,000 years of transit time and 4.6 billion years of planetary and biological and cultural evolution to be received and comprehended. Every prior generation of humans lived and died without knowing what the center of their galaxy looked like. Every observation Webb made was a first, the first time that specific piece of information crossed the boundary between unknown and known. That boundary is not a line. It is a frontier, vast and irregular and constantly shifting as instruments improve and theories develop and new observations push the edge of the known into territory that was previously inaccessible. The galactic center, which seemed on the verge of being fully mapped and understood before Webb turned its mirrors toward it, proved instead to be a treasury of unexplained phenomena, demanding new theoretical frameworks and motivating new generations of observers to design the instruments and missions that will follow Webb into the infrared sky. Somewhere in that frontier, in the gap between what Webb revealed and what remains to be understood, lies the answer to why Sagittarius A times is silent. The complete explanation for how stars form inside the tidal radius, the full history of the black hole's awakenings and dormancies over 13 billion years, the nature of the intermediate mass objects orbiting in the central parsec, the mechanism that maintains water vapor in a radiation environment designed to destroy it, the source of energy, ionizing neon in regions where no known ionizing source is sufficient. These are not small questions. They connect to fundamental issues in physics and astronomy, to the theory of gravity in strong field regimes, to the chemistry of the interstellar medium in extreme conditions, to the formation and growth of the supermassive black holes that govern the evolution of every large galaxy in the observable universe. Answering them will require the next generation of space observatories, ground-based telescopes with adaptive optics, more sophisticated than any currently operating gravitational wave detectors, sensitive to the frequency range produced by black hole mergers in galactic centers, and theoretical frameworks that may not yet exist in even embryonic form. The work is enormous. The questions are hard. The answers will not come quickly or easily or all at once. They will come the way all genuine scientific understanding comes, gradually through the accumulation of precise measurements and careful analysis, and occasionally the sudden recognition that data previously considered independently actually fit together into a coherent picture that no one had anticipated. This is the situation Webb has created at the galactic center. Not a solved problem, but a more precisely framed one. Not a complete picture, but a far more detailed sketch of what the complete picture must ultimately contain. Not closure, but the productive opening of questions that will occupy astronomers for decades, perhaps for the remainder of the century, perhaps beyond. The monster at the center of the Milky Way has been sleeping. But sleeping things dream, and in the dreams of Sagittarius A, times in the protostellar births occurring impossibly in its shadow, in the clumps of gas, spiraling toward the event horizon in the ancient ionization, echoing through clouds, scattered across hundreds of light years in the enormous bubble structures preserving the memory of its last great awakening in all of this. The future is assembling itself with the patience that only something measured in geological and astronomical time can afford. We are watching, from our quiet location in the outer spiral arms at our borrowed distance in our borrowed time. Instruments that took decades to build and 1,000,000 miles of space to position have given us eyes capable of seeing through the dust that hid this heart from every prior generation of human observers. What we have seen is stranger and richer and more complex than anyone expected. What we have seen demands humility, not the false humility of self-deprecation, but the genuine humility of recognizing that the universe contains depths, that our best theories only approximate mysteries, that our most powerful instruments only partially illuminate 26,000 light-years away in the direction of the constellation Sagittarius. A 4 million solar mass black hole sits at the center of the galaxy in which you live. Around it orbit stars moving at millions of miles per hour. In its shadow, new stars are being born in defiance of every equation written to describe why they cannot be. Gas flows spiral toward an event horizon that nothing, no matter no light, no information of any kind, crosses outward. The silence is vast and deep and, by every measure we possess, temporary. And you are made of the same material that orbits it. The same chemistry, the same stellar ancestry, the same galactic history. The atoms in your body have been part of stars, part of supernova explosions, part of the interstellar medium drifting through the spiral arms of the Milky Way for billions of years. Some fraction of you has passed through the extreme environment near the galactic center, been processed by conditions that no laboratory on Earth can replicate, and traveled outward on galactic winds to eventually participate in the chemistry of a world where awareness became possible. The center of the galaxy is not distant in any way that matters most. It is your origin written in atomic ratios too small to see but too fundamental to ignore. It is your context, the gravitational anchor around which your sun has completed 20 orbits in the time since it formed. It is your future, in the sense that the awakening of Sagittarius A times will shape the galaxy your descendants inhabit long after the specific configuration of matter that constitutes you has dissolved back into the interstellar medium from which it came. Webb showed us this center as it was 26,000 years ago, with the clearest eyes humanity has ever built. What it showed us is that the heart of the Milky Way is alive in ways we did not expect, complex, in ways our theories did not fully anticipate, and mysterious in ways that will continue drawing human curiosity outward and inward, simultaneously for as long as human curiosity exists to be drawn. The monster sleeps, the silence holds, the ingredients for awakening accumulate in the darkness at the center of everything we orbit. And the light from that darkness, ancient by the time it reaches us, carries news of a universe more intricate and more astonishing than the one we thought we understood. It always does.